So now we have Paul Grigas, who's going to give us the last talk of the day, and then we'll have our masters, and then we're going to do our graduation at the USC Club. So make sure to come to that. Paul is a graduate of MIT and the faculty at Berkeley IOR. A recipient of several awards like the Optimization Society Student Paper Prize and the Informed Paper Prize. And he'll talk to us today about his work in predicted optimized setting.
Thanks, Adam. Thanks everyone for sticking around for the last talk. So today, the goal of my talk is to really give you a tour of this line of work that I've been working on for several years now, since when I was a PhD student, essentially when I started, on the predicted optimized setting. So the talk will be based on these 4 papers. And first, let me acknowledge my collaborators, Othman El Balghiti, Elmachtoub, Ambuj Tewari, and Heyuan Liu. So basically, I will first give a brief overview of my thinking about the predicted and optimized setting. So some of this will build on ideas already introduced by Brandon, Priya, and Brian, but I'll just introduce my notation and such. And then I'll talk about what I've done in this setting, which has really been, in my view, some sort of foundational work on statistical and optimization properties and results in this setting. So let me also mention that the second half of the talk basically will be largely focused on the newest work here, which is this work on adapting some of these ideas to the online contextual decision-making setting. And this is really joint work with my excellent PhD student, Heyuan Liu. So I just want to acknowledge his work here. Okay, so first, as I said, I'll introduce the predict and optimize framework. Then I'll talk about our main computational approach in this setting, which is a surrogate loss function we call the SBL plus loss function. I'll talk about some statistical properties of the function, in particular consistency results, as well as what are called risk bounds. And then I'll talk about this online contextual decision-making setting where we adapt ideas of SBL and SBL plus to online decision-making. Okay, and then some conclusions in future directions. So as we know by many of the talks today, essentially all of them, large-scale optimization problems arising in practice almost always involve unknown parameters that can be predicted based on contextual information. So the classic approach here is the predict and optimize approach, where we first predict the unknown parameters and then optimize given the predictions. And classically, these 2 phases, prediction and optimization, are completely decoupled. So there's an obvious opportunity that many of us have capitalized on, and many of us will be able to in the future, because I think there are a lot of open directions here. There's this opportunity to basically bridge these 2 phases together to design prediction models that are informed by the downstream optimization task. So here are just 2 examples. So one is maintenance scheduling. So imagine you have a collection of machines or vehicles that you need to maintain or repair over time. The optimal maintenance schedule can be determined by a shortest path problem. And the exact maintenance costs, which would represent the edge costs of this shortest path formulation, are unknown, but may depend on features like seasonality, demand, economic indicators, et cetera. Or you can think of a real routing problem like Google Maps or Waze, where they recommend routes to people based on their predictions of the travel time along this network. They solve the shortest path problem, but ultimately they're using predictions of the travel time to solve that shortest path problem. Another example is portfolio optimization, where the returns of different assets are unknown, but may depend on contextual features like historical returns, news, again, economic factors, and so on. So again, the standard approach here is first predict these unknown parameters using machine learning, and then plug the predictions into an optimization model and solve. And this is what we really refer to as predict and optimize. So I want to highlight here, some fundamental statistical and computational concerns for what we call a smart predict and optimize approach. And this is an approach that takes into account the fact that the predictions are used as input to this downstream optimization problem. So how can we leverage the structure of this downstream problem to make better predictions? So specifically in this talk, I will focus on optimization problems with a linear objective. So I consider this stochastic contextual optimization problem where I want to minimize with respect to W the expectation of a linear function, objective function, conditioned on some feature vector X, right? So D sub X here is the conditional distribution of the vector C given our auxiliary feature or auxiliary context X that we observe. S here is a given and completely known convex and compact set. So I assume, at least for now, that the constraints are completely known. We want to somehow use the structure of S, the structure of this optimization formulation, to think about how to make predictions for C based on X. And there are many approaches now for thinking about how to do this in the literature. So I won't give a full or even partial literature review here, but I'll just mention that historically, like, before we really started thinking about this problem, most of these approaches were focused on very specific problems. So either problems without constraints or with very simple constraints. Or there are, sort of classical approaches that did not account for the optimization structure. Now there are various different approaches, many of which were talked about today, that do account for the constraints in non-trivial ways, and I'll present our approach based on SPO plus. Okay, so one thing to notice from the linearity assumption that makes things very convenient here is that by linearity of expectation, we can just say that the minimization of the conditional expectation is the same thing as minimizing one particular linear optimization problem given a very special cost vector, right? And that special cost vector is the expectation of C given X, right? So all else being equal, right? If we knew this conditional expectation of C given X, we'd be done, right? So in a sense, that would be great, right? So what it really comes down to, right, is how do we estimate this conditional expectation function in a way that accounts for the structure of the feasible region S, right? But what this relationship shows is that really estimating this conditional expectation function is sufficient, right? So that is one way to think about our objective here. Okay, and then once we have a function or an algorithm, a machine learning model for doing this estimation, then we can use it to go back to the optimization problem and plug it in, right? So given any prediction C hat based on some machine learning model, right? So C hat is some prediction given an observed context. The predict and optimize process basically says we plug in C hat into this problem, and that should be a C hat up top minimize C hat transpose W subject to W and S. And then we make our decision, W star of C hat, right, depending on this prediction. But then the cost that we incur is ultimately with respect to the true or realized value of C, right? So the cost that we incur is C transpose W star of C hat, right? So, so to summarize sort of the key ingredients of our framework, we have this downstream linear optimization task, minimize C transpose W subject to W and S. We have historical data that we can use to build a model. The data consists of pairs of context X and cost vector C. We'll also assume that we have a hypothesis class of cost vector prediction models, right? So this is a class of models F that take context as input and output predictions for C, right? So F of X is equal to C hat. And we also have a loss function that quantifies the error in making a prediction of C hat when the actual realized value is C, right? So what this really will come down to is how do we determine the loss function? And so to sort of motivate how to determine the loss function, I want to present a simple geometric picture, right? So here's the case of S being a simple polyhedron, simple polytope in 2 dimensions. And what I've drawn here is the negative of a particular cost vector, right? So the negative of some cost vector C. So it turns out that the optimal solution corresponding to C is that star, right? The star up top. And drawn around C is a level set of the L2 loss function, right? So in other words, a circle. So that's a level set of the least squares loss function. And so what that means is that these are all the points where the least squares loss is the same around the true value of C, right? So a least squares loss function, right? A loss function that might give you a prediction of C hat A or might give you a prediction of C hat B. With respect to the least squares loss function, those two predictions are exactly the same, right? So those two predictions are completely indifferent with respect to the least squares loss. On the other hand, though, we can see that geometrically, those two predictions lead to very different solutions, right? So C hat A actually gives you the right optimal solution, right? You recover the correct extreme point. C hat B, on the other hand, gives you the optimal solution down here. So least squares loss, if you were to use that as your loss function, it may give you, an incorrect optimal solution. On the other hand, we really know that everything that's in that cone, right, everything that is agreeing with the optimal solution corresponding to C would actually give you zero cost with respect to the ultimate downstream optimization task, because it would give you the correct solution. Right, and you can tell a sort of similar story in non-polyhedral cases, but I'll skip the details for now. All right, so what this geometry sort of motivates is that really we would like to have some type of loss function that agrees with the decision error, the regret of the downstream optimization problem. So let us first define what that regret exactly is. So we call it the smart predict and optimize loss, the SPO loss. And it's exactly the regret with respect to this process, right? So it's the cost of making a prediction C hat and making a decision corresponding to that prediction, W star of C hat, evaluated on the actual realized cost vector C, minus the optimal cost in hindsight, right? So the SPO loss is exactly the cost that you incur due to having a prediction C hat, which might lead to a suboptimal solution, minus the optimal cost in hindsight if you had perfect knowledge of what the correct cost vector C should be. Right, so think it's the travel time that you actually incurred along the network when you went about your route, minus the travel time if you had known ahead of time what the optimal route would have been. So in some sense, this is the ideal loss function for the decision-making task with respect to the feasible region that we're given. And so ideally, we might want to solve this empirical risk minimization problem with respect to this loss function, right? We might want to pick a model F, which minimizes over our hypothesis, the empirical version of the SPO loss. And that's the problem that I wrote down here. Okay, so just to give a little more intuition, we can actually show that the SPO loss here is a special case of the classical 0-1 loss in binary classification. So this simple equivalence happens when S is just an interval and the cost vector distribution is supported on labels of -1 and +1. So in that case, the SPO loss corresponds exactly to the loss, which gives you a loss of 0 if you make a correct prediction for the label, and a loss of 1 if you're incorrect. And this type of reasoning of this example can be generalized to multi-class classification when S is now the unit simplex. And just as a preview of what's to come, this SPO plus loss, which I'll introduce in a moment, ends up being equivalent to the hinge loss of SVM in this case. So that's the orange loss function there, which is has a negative slope when the x-axis is less than 1 and 0 when the x-axis is greater than 1. So you see that this hinge loss has a gradient which is pointing down when you're making an incorrect prediction, right? So in some sense, that's sort of desirable for thinking about how to get to a model that makes better decisions, and I think provides a little bit of intuition of what SPL plus is doing. Okay. Any questions so far? Yes.
I'm just wondering about alternative definitions. So you don't know C.
Right.
So if you look at alternative definitions, which just compare all pair.
Right. So sure. You may have some classic multi-class classification thing where you look at all pairs comparisons, things like that. Problem with that in typical application setting here is that you're going to have an exponential number of pairs, right? So we're going to really be concerned with, or even possibly infinite in continuous problems. So we're going to really be concerned with, polyhedral examples where you're not given the extreme points explicitly. You're given inequalities.
Right, but since you don't know the C, how do you do the evaluation?
So we assume that we have historical
synthetic problems, then you can always.
So we assume that we have observed in the past the correct value of C. So think, Google Maps has observed what the actual travel time was, but that was only in the past.
No, but you observe C1, C2, C3, so on. So are those? Do you just pick one of them as a C?
No, so we're trying to find a model for making predictions for future Cs based on the past C that we observed. Good. Okay. So let me continue. So now let me formally define what our SPO plus surrogate loss will end up being, and sort of motivate it. So it turns out this SPO loss is non-convex and in fact can be discontinuous depending on the structure of S. In the polyhedral case, for example, it is discontinuous. Actually, Brian showed a nice picture before illustrating why that discontinuity happens. And so therefore, this optimization problem is challenging even for simple hypothesis classic linear functions. So there are a lot of ideas now for how to make this optimization problem more tractable. Brandon, Priya, and Brian all presented different approaches for that in their settings. The approach that we advocate for here is the use of a surrogate loss function. So we're motivated kind of by the connection to binary classification and the classical idea of machine learning, where you replace this difficult 0-1 loss function with a more computationally friendly surrogate. And in particular, the surrogate that we introduce ends up being a convex function. It also ends up upper bounding the original SPO loss. So the SPO plus is an upper bound and it's also convex. And this is just like the hinge loss of SVM. It's just like many other surrogate loss functions. These are two desirable properties. Now, the formula looks a little bit unintuitive, and it definitely is at first sight. But let me provide a little bit of intuition, or try to. So first of all, where it comes from is a sort of duality argument. So we provide in our paper a dual interpretation of the original SPO loss and somehow derive this surrogate from that interpretation. And some of the intuition for what it's doing comes from this picture. So think about the case where you're actually making a prediction C hat, which leads to this correct optimal solution given the realized value of C. So that means that C and C hat lie essentially in the same normal cone generated by this extreme point. In that case, as long as the prediction C hat is sort of sufficiently large and it lies in the same cone, what I write here as points in the same direction, then it's going to be the case that the optimal solution to this maximization problem up here, maximize C minus 2 C hat transpose W, will agree with C, right? So it'll be the same extreme point up top. In fact, all three will be the same, right? So W star of C hat will equal W star of C will equal W star of 2 C hat minus C. And so what that means is that after some cancellation up top, this SPO plus reverts exactly to the SPO loss, right? So this means that for favorable situations where you're making the right prediction, SPO plus is exactly the same as SPO. And in sort of non-favorable situations, my intuition goes back to the hinge loss, where the SPO plus kind of gives you a gradient which is pointing downwards, right? It's helping you to identify a better optimal solution than the one that your parameters are currently giving you. Okay. Yeah, so that's a little bit of intuition, but perhaps more importantly, at least from a theoretical point of view, we can derive some statistical guarantees that relate the SPO plus formulation to the original problem of interest. So to do this, we consider first the problem of Fisher consistency, sort of the most basic type of result that we could hope for here, which asks a very simple question. Assume we have full knowledge of the data distribution, right? Assume that we know exactly what the distribution of X and C should be. So that's a very ideal situation, so that you can think of this kind of as a sanity check. In this sanity check ideal situation, if we actually minimize the expected risk with respect to SPO plus, do we recover a solution for the expected risk with respect to SPO, the decision cost that we care about, right? Does the surrogate work in this super ideal situation? That's what Fisher consistency is asking for. And this is a classical property of statistical models. So it's been demonstrated, for example, for the SVM hinge loss to show that it's consistent with respect to the 0-1. Also, there have been lots of work in structured SVMs examining similar things. So structured SVMs are a version of multi-class classification, examining various conditions for different forms of consistency. So the theorem that we provide in the original paper of Adam and I is that under the assumption that the hypothesis class that we're working with contains the sort of ideal correct prediction function, the expected value of C given X, and under the assumption that the distribution of C given X has a positive density everywhere and is centrally symmetric about its mean. So think a normal distribution, but a generalization of that. Then minimizing the SPO plus risk also minimizes the SPO risk. And moreover, the expected value of C given X is the unique such minimizer. Okay. So this verifies the Fisher consistency property, which is nice. And we have examples demonstrating that we need sort of both of these assumptions on the conditional distribution of C given X in order to establish this Fisher consistency result. Okay, so we like to also sort of strengthen this result if we can. And so this is what I looked at a little bit more recently with my student Heyuan. So here, the previous result is really assuming that you have full knowledge of the true distribution of the data. In reality, you don't have that, right? In reality, you actually have a finite amount of data, which means that you can only solve the expected SPO plus problem to some finite precision, call it delta, right? So, so based on a finite amount of data, we can hopefully get the excess SPO plus risk to be less than or equal to delta. And so the question here is, does the excess SPO plus risk being small, less than or equal to delta, guarantee that the excess SPO risk, right, the difference between the SPO risk of your function f that you're estimating minus the optimal such risk, is that difference going to be less than or equal to some epsilon, right? And so this is the question of a risk bound, which is a quantitative version of consistency. And risk bounds like this have been established for least squares and related surrogate losses in these works. So we show such bounds for SPO plus. So basically, in the polyhedral case, again, under the same assumptions that Adam and I made, plus a few additional assumptions on the structure of the distribution, we showed that the SPO plus risk satisfies a risk bound like this with delta scaling like order epsilon squared, meaning that if you want the excess SPO risk to be less than or equal to epsilon, you need delta equal to epsilon squared. And we also show that this result is tight in the polyhedral case and can be improved to an order epsilon result under additional strong convexity assumptions about the set. So under sort of more favorable geometry, you can actually improve this result, but at least in the polyhedral case, we get a result which is tight. Yes, question.
Yeah, so I'm curious. So this condition that the conditional distribution essentially is symmetric. In your experience, like, do you think of this as more sort of like a technical condition that really doesn't matter that much, or are there cases where if the distribution is very skewed, like you might actually, want to like change the method somehow to accommodate that?
There are cases where if the distribution is skewed, you might want to change things. Yeah, yeah. So there are cases. I mean, like simple cases in one dimension, where if the distribution is skewed, you will converge to the wrong thing, right? You won't recover the expectation of C given X. So yeah, so I think to me what it sort of highlights is that, and this is a point that I think is really important in general here. Using SPO plus alone may not be the best thing to do, right? So instead, in practice, a good idea maybe to combine SPO plus with least squares or some other more classical thing, just kind of correct these sort of issues. Then you may hopefully get a best of both worlds type of thing where you have something that accounts for the structure of the downstream problem, but you also have something which is kind of correcting for the magnitude of the predictions and fixing these sort of issues. Yeah. So in practice, that's really kind of what I advocate for, actually. Good. Other questions? Okay. So I just want to also briefly touch on the topic of generalization. So I only have a 2-slide summary of this. So generalization is sort of an even more basic question than the consistency question. It goes back to the question of just looking at the SPL loss itself for any given model, right? Forget about SPL plus. Maybe you train the model with least squares, or maybe you just randomly pick the model, or maybe you did train it with SPL plus, right? Whatever model that you pick, if I evaluate its empirical SPL loss, right? If I look at my data that I have and I look at the decision error that was evaluated on the data, does that empirical quantity actually resemble the expected loss on the distribution, right? Does it actually resemble the cost that you expect to pay in the future when you actually go to deploy the model? That's what generalization bounds are asking for. And so we established, the first generalization bounds for the SPL loss in this paper, and in two situations, right? So basically, we established combinatorial bounds that rely on essentially converting the problem to a slight extension of multi-class classification. These bounds may have relatively bad dependence on the dimension. We improved this dependence using margin-based arguments that are more non-trivial. So I'll not talk about any of these details. I just want to mention that this is sort of an important topic in my opinion, because one thing we can always do in practice is evaluate the model on the data that we have, and we like to be able to say that that number that we get from doing this evaluation is close to the performance that we expect to see in the future. And establishing generalization bounds is a way to theoretically validate that type of reasoning. So this is a topic that we looked at as well. Okay, any other questions before I move on? Okay, so I think I'll actually skip these computational experiments because I'll also present some computational experiments for this next part, which are somewhat similar. So I want to spend the next 20 minutes talking about this extension to online contextual decision-making, which is very recent work just posted on arXiv last week, joint with my PhD student, again, Heyuan Liu. So to motivate this one, we're still kind of in the predict and optimize setting, but now we're thinking about an online version. And so we're thinking about a decision-making problem that has these sort of common features. So first, decisions must be made sequentially over time. This is the online aspect. And furthermore, you can think that there are some resources that you have a budget of that are consumed every time you make a decision, right? So depending on the decision that is made, a budget of m different resources may be consumed. And so due to the limited amount of resources that you have, there is now a trade-off between immediate rewards and rewards in the future, because making a decision right now affects the budget that you have left for decisions in the future. Furthermore, in this situation, the rewards, as well as the amount of resource consumption, is not available directly at decision-making time, but may be predicted based on contextual information. And here's where the predict and optimize part comes in. So some example applications that you might think about are routing with congestion constraints. So think about Waze or Google Maps. They're providing a bunch of different recommendations to people on a network. And the recommendations that they provide ultimately affect the travel time or the congestion on that network, right? Another example is bidding in online advertising. So online advertising campaigns have a certain amount of budget that they want to use across different impression types. And thinking about how to do that optimally depends on predictions that are made for quantities like the click-through rate, which depend on contextual information about the ad and so on. Okay, so formally we consider this sort of problem setting. So we have an online problem with t different rounds or t different time horizon of capital T. There is still a feasible region S. Here I call it script S to be consistent with the notation. There is a feasible region S for our decision variable W. And now there's also something called a resource consumption feasible region, script V, and also a concave resource consumption utility function U. And at time t, we first observe a context vector xt. We then make a decision, wt and s, based on this context. Then we observe a reward rt and a consumption matrix vt, which comes from some conditional distribution given the context. And then finally, we incur the reward that we based on the RT that we observe, right? So we receive or incur some reward RT transpose WT and incur resource consumption amount given by this matrix VT transpose times WT. Right, so again, RT transpose WT is the amount of the immediate reward that we receive, which is a linear function of W, and VT is the amount of, VT is a vector with one component for each resource, which gives the amount of resource consumption observed at that time. Yes.
See if this is as a Markov decision process in a way.
Perhaps, yeah. Perhaps you could think of it that way. Yeah. Yeah. Yes.
So is the setting, is it like a stochastic setting or adversarial?
Yeah. So we will consider a stochastic setting. I'll get into those details now. Yeah. Yes.
So does it look like this is online linear programming, but I get a context? Is that
Exactly. Online linear programming with a context. Yeah.
And
Yeah.
when are the budget constraints enforced?
I'll get to that right now. Yeah. Okay. So so basically, the ultimate goal of the decision maker is to maximize after 2 rounds the summation of the average reward and the utility of the resources consumed. So R average is the average of the rewards that we incur. V average is the average of the resources that are consumed. This is completely equivalent to maximizing the total reward plus some total utility. Here I just do average for convenience to describe the theoretical results. But it's completely equivalent, you can think, to maximizing the average reward plus some utility of your total resource consumption. At the same time, in addition to this utility function, you also have a hard constraint, which says that the resource consumption must remain in this set script V. So you can think, if you like, that the set script V is just usual budget constraints, right? So it's like the set of V less than or equal to some budget vector B. And in which case, this hard constraint is enforcing that you don't go over the budget constraints. Yes.
but when is it enforced?
I'll get to that. We consider 2 cases. So we consider basically hard constraints where you must stop the algorithm as soon as you leave the set, and we also consider soft constraints where we look at bounding the infeasibility. Yeah. Good. Okay. So actually towards that direction, how we think about this problem then is in a typical way, sort of where we want to look at a sort of penalized version, right? So we consider this penalized version where we maximize the average reward plus the utility minus some penalty parameter psi multiplied with the distance to this set V, right? And the convenience of this penalized version of the problem is that we can look at its primal dual form by taking Fenchel conjugates. So basically, if you consider the Fenchel conjugate of the utility function as well as this distance function, it leads to this primal dual form. Skipping some details, in case you're not too comfortable with Fenchel conjugates, that's okay. The important point is that at the end of the day, what it boils down to is a linear optimization problem. Right? The main benefit of taking this Fenchel conjugate of the utility and the distance function is that it exposes the linear structure of the problem. And what we get in our online algorithm is at every step, we must solve a linear optimization problem over this set S, right? But now the linear optimization problem is not just depending on the reward vector RT, which I'm kind of thinking of as the cost vector from before. It's also depending on some multiple of the resource consumption, actually 2 multiples of the resource consumption, depending on dual variables, right? So we essentially dualize the hard constraint as well as the utility function to get a linear problem that we solve to make a decision. And then after we make a decision according to that linear optimization problem, we update the dual variables using online gradient or mirror descent. Okay, so that second part is really kind of a standard idea, right? The idea of updating using online mirror descent is kind of standard. The novelty of what we're doing here is that we're thinking about using SPO type methods for predicting the cost vectors at each stage of this process, right? So as I said, this primal dual form kind of exposes this linear structure. And so what we see is that at every time, there is really a cost vector CT, which is the reward vector minus this VT times some dual variable. And when we're given a context XT instead of the exact information of RT and VT, what we really need to do in order to make a decision is predict this cost vector CT based on the context. But this is exactly a linear optimization problem and fits quite nicely into the predict and optimize framework, right? And so therefore we can adapt SPO algorithms to this setting, right? And that's what we're going to do. Okay, so to be a little more careful then, our algorithm is essentially combining a prediction and a decision-making step, right? So at every time we observe a feature vector XT, we make predictions according to some model for the reward and consumption, R hat T, V hat T, and then we make a decision according to this linear optimization, which depends on our prediction as well as the dual variables. Then we update the dual variables using online mirror descent or online gradient descent, if you like. And the specific functions are the differential functions that I introduced before. And then we update the predictor F hat T plus 1 by using the past observations to perform empirical risk minimization of a surrogate of the SPO loss, right? So we look at these past observations of cost vectors. We consider a surrogate of the SPO loss, L, which could be the SPO plus loss, it could be least squares loss, it could even be the SPO loss itself, if you can actually optimize that. And a hypothesis class H, which gives us predictions R hat, V hat. And then we update our next prediction model by using the past observations as historical data and plugging those past observations into the surrogate loss function. Yes.
Is this full information feedback?
Full information feedback, yes.
Okay.
Yeah. We observe, after we make the decision, we observe the full vector RT, the full capital VT, yes.
So when we're making a decision this time step, we're not thinking about this next time steps?
No, we might be thinking about the next time steps, yeah. I mean, that's where the dual variables come in, right? So the dual variables help us to think about how much of the budget we have depleted and how we're doing with respect to this utility function that we care about. Yes.
So this, so do you have like T plus 1 and T plus 2 and so on when you're deciding the W for WT?
Well, we haven't observed. Well, when we're deciding the W, we decide the W from a linear optimization problem, right? But the linear optimization problem is changing its. It's not like if it was just using R hat T. If the dual variables were 0, and we ignore that second part, it's like it's being greedy with respect to the current time, right? So that would be the sort of greedy algorithm. But here, because we're introducing this other term, the dual variables are accounting for essentially how tight the budget constraint is. Yeah.
So is the regret here calculated in terms of just the regret in terms of reward, or the regret in terms of reward plus the valuation?
Let me get to the regret bounds right now. Yeah, thank you. Yeah. Okay, so to establish the regret bounds, we need to first make an assumption about the surrogate loss that we use. And what we do is we assume that this empirical, we basically build upon the previous statistical results that I presented before for SPO plus. So we assume that the empirical surrogate loss minimizer has a uniformly small excess true SPO risk, which holds uniformly over the dual variables. So this assumption holds for SPO plus because of the calibration results that we proved in the previous paper, as well as results about generalization of SPO plus, as well as the fact that the dual variables are bounded. So that gives you the part that it's uniform over the dual variables. Similar results also hold for L2 and any sort of classic loss function that you might consider. Okay, so that assumption is expected to hold. And then in terms of the regret, we compare against a benchmark policy, which is sort of the optimal context-dependent static policy, meaning that it's a policy pi which maps you from features to decisions. And given any such policy pi, we can look at the true expected reward, which is the expectation with respect to the true distribution of R transpose pi x, and we can look at the true expected consumption, which is again the expectation with respect to the true distribution of V transpose pi x. Then the optimal such static policy is the one that is the supremum over all policies of the expected reward plus the utility of the expected consumption, subject to the expected consumption being feasible. Okay, so this optimal static total reward is a standard benchmark in the literature, and it's can be that this is an upper bound on the total reward of an optimal adaptive policy, which adapts to the past data. Okay, and then in our analysis, we consider two cases. So a hard constraint case where we stop the online algorithm as soon as the resource constraint is violated, right? As soon as we leave this set script V, the algorithm terminates, as well as a soft constraint case where we want the infeasibility to be the distance to the set V to be small.
For the
Yes.
hard constraint case, how is then the average reward? Is it still 1 over capital T?
Yes, yeah,
Okay.
yeah. So it's 1 over capital T, but it sums up to a stopping time. Yeah, so the stopping time is now the time where we leave this set script V, and the average reward would be 1 over capital T. In our analysis, we also will use a constant B script V, which is the distance from 0 to the boundary of V. Okay, and so the theorem that we prove is that the online algorithm in this hard constraint case has this guarantee where the suboptimality of the reward at the stopping time plus the utility of the resource consumption at the stopping time average is less than or equal to something which is O of some constants. So the constant is the budget parameter plus the Lipschitz constant of the utility plus this C risk constant, which comes from our learning guarantee assumption, times two terms. So one term that depends on the speed of the learning process, that depends on the structure of the surrogate loss function, and another term which is O of t to the minus 1/2, 1 over square root of t, which is really the regret from online mirror descent. So basically our analysis is all about decomposing the regret into these two different types. One which comes from the regret of analysis of the online mirror descent method or some online primal dual method, and the learning theory guarantees that we have established for surrogates of the SPL loss in the predict and optimize setting. Yes.
So if you have the stop, then should there be some penalty for it? Then there's some kind of bias.
So right, that's a great question. So so notice that we have something kind of hidden up here, which says that the penalty parameter must be larger than this OPT value divided by BV. And the BV is like the distance to the boundary of the set V. So if in the situation you're thinking about, BV is going to be very small, which means that the penalty parameter must be very, very big, which leads to a big constant over here. So there's no free lunch. Yeah, so that's what happens. Yes. Okay. So we also analyze the soft constraint case. In the soft constraint case, we make this additional assumption. And this additional assumption is actually really just something about this. Essentially, sort of comes from a Slater condition on the problem, and it basically says that if we consider a relaxed version of the problem, where now instead of imposing the hard constraint, we say that the distance to infeasibility is less than or equal to epsilon, then we have this type of subgradient condition, and this can be validated under a Slater condition and sort of standard convex analysis arguments. And so under that assumption, then we also, in the soft constraint case, prove first a bound which is similar to the bound from before. So a similar bound on the regret or the suboptimality, which depends on these two things, as well as a bound on the expected distance to infeasibility, which is again O of t to the minus alpha plus t to the minus 1/2. Okay, let me show some numerical results to conclude. So in our numerics, we compare the performance of, so we're looking at this online algorithm basically algorithm 1 here with different choices of surrogate loss function for updating the predictor function, right? And so the different choices of surrogate loss function that we consider are SPO plus, least squares applied to the cost vectors CT that are induced by the dual variables, as well as least squares directly on RT and VT. And we also consider as benchmarks, so the ideal benchmark that we compare everything against is the algorithm which actually has perfect information. And then we also compare against SAA, which just ignores the features, as well as the ground truth model. So these are just benchmark comparisons. The real comparisons are against the different surrogates. And the first example we consider is a resource allocation problem. Here, the decision space is just a hypercube, and the budget constraint, so the resource consumption is just budget constraints, and it's a hard constraint case, so all the methods stop when any constraint is violated. Okay, so the results that we see are here. Let me zoom in on the results for the linear case, so linear hypothesis class. What we see, so SPO plus is the one in blue, and the L2 applied to the cost vectors, least squares, is the one in red. And really, those are the two to pay most attention to. So purple is this true model. So that's assuming that you have the actual conditional distribution, which is not viable in practice. It's just a benchmark. So we see here that as the number of iterations, capital T, on the x-axis gets larger, both of these are converging to a relative regret of 0, right, relative to the perfect information policy. But SPL plus is providing significant benefits, especially when the sample size is small, but even for larger sample sizes. SPL plus, which is using the structure of S, the downstream optimization task, is providing benefits above the standard least squares. And the top two are just SAA and least squares applied to RT and VT directly, which are really not competitive. SAA is not even guaranteed to converge, and the other one is converging very slowly. Okay. We also see similar results on shortest path, or rather longest path problem. Here we have a non-trivial utility function. That's the main difference. So the utility function is something that is sort of encouraging or discouraging congestion. And here we try a different data generation mechanism where we try nonlinear dependence of C on X. And we observe basically that as this nonlinear dependence increases, we observe a stronger performance of SPL plus relative to everything else. This is something very similar to what Adam and I observed in the original paper for SPL. Okay, so to conclude, I reviewed here the predict and optimize framework as I think about it, and presented some sort of tour of the different problems that I've been looking at in this setting with different collaborators, including Fisher consistency of SPL plus, as well as stronger risk bounds, some discussion of generalization, and this extension of looking at SPO type algorithms in the online decision-making space. I'll just mention that I think there are many, many exciting future directions. I mean, one obvious one to mention, which was discussed here, is incorporating banded feedback into this type of online setting. So this is a full information feedback setting. Incorporating banded feedback, for example, would be very interesting, and many other exciting ongoing directions as well. So thanks everyone for your attention, and I'm happy to take further questions. Yeah.
Hey, yeah, thanks for a great talk. I guess a question I have, I'm sorry if I missed it, is the online contextual decision-making setting, is the assumption that the distribution of costs over time is independent of the decisions that you actually end up making, or is there sort of a potential dependence in the sense that your costs could actually change based on the decision?
Yeah, good question. Yeah, that distribution is constant over time.
Okay.
So yeah.
Thank you.
Yes.
Just a comment on the future directions. So if you think of like Google Maps, right, it may not be exactly sequential decision making, because if you make sequential decision making, it's not going to work.
Right.
No, at the scale.
Yeah.
So you might need something which is not exactly sequential.
Right, some kind of batch decision making or something. Or it's, yeah, I agree. Yeah.
Otherwise, it's not going to work.
Sure. Yeah. Yes, be sure.
So was there some advantage of not including at least the hard budget constraints straight into S? Like he teased out that, I mean, it's also a form of a hard constraint beyond the utility over the source.
Right, okay, but so the problem is, I mean, we are assuming here that the way that the decision impacts the hard budget constraint through this capital V is not known, right? So it's something that is predicted, right? Or something that is random and ultimately predicted. So you can kind of think about this as a first step towards SPO or differentiable optimization with things in the constraints. But it's a very toy model for doing that. So I think there's still a lot of open questions about that. Yeah.
So I'm trying to understand these results in context of the online learning for linear programming, like online linear programming results. So they're also looking at the same notion of regret. And I thought those results are tight. So is the answer here that we're getting something that's like better in the constants? Or sorry, rate type. I thought those results are regret.
Yeah, so we're not really improving on the rate. In fact, the best that we can do is match that rate, right? Because we have this minus alpha, which depends on the on which surrogate you're using and so forth. This is really about
the type rate is 2 to the 1/2.
Yeah, 2 to the 1/2 is the type. Yeah, that's the type part. So this is really showing that.
The finite time behavior is better.
Yeah, exactly. So somehow accounting for the structure of the optimization is better in finite time, just like with limited samples and in standard setting, it's the same thing.
Thank you.
Yes.
All right. Thank you.
Okay, thanks.